may be intrigued by the title. There's a well-known phrase, lies, damn lies and statistics. And an American statistician called Paul Fieleman wrote an article with that title, Truth, Damn Truth and Statistics, about the history of the origin of the phrase lies, damn lies and statistics. So that was where it came from. I worked in a variety of contexts with statistics as an applied statistician, but I'm also a scientist and engineer. So I'm self-taught in stats, and I've done an awful lot of rather peculiar stats over the years with peculiar data that has been presented to me by various people. So I regard myself as a rather sceptical guy who's a problem solver. Right, if we can get this to work. So my first slide beyond the title slide is basically to illustrate the fact that statistics isn't just about data analysis. It's especially powerful in other areas as well, like designing your study and a variety of other areas, like how many samples should I take, for example, how many measurements should I take. So I wanted to draw your attention to it by this rather silly cartoon, just to make the point. So I ran a course in Birmingham University in the Faculty of Science and Engineering some years ago, where I was invited to design a special course for natural science students called Statistics and the Scientific Method. So I'm particularly interested in the way it locks into the way we do science and engineering and how it should theoretically underpin it. So I'm particularly concerned with these various statements here. So we're often concerned with testing hypotheses and with the means of testing them. Now, there are a range of schools of statistics, and we have theological arguments with one another about whether one way is better than another, but that's, as far as I'm concerned, not the point of my talk. A lot of modern statistics is about ways of exploring data to find meaningful patterns, and however you do it, whichever approach you take, that's one of the aims that we're interested in, turning data into useful information. One of my areas of interest is in how we display that, so statistical graphics is of particular interest to me. A lot of modern statistics is what we call data-driven. So there was a famous industrial chemist in Britain who went over to America and turned into one of America's leading statisticians, a guy called George Box, who is famous for a phrase, all models are wrong, but some are useful. And that's how we're trying to describe the world around us. We're trying to create a model out of the data we acquire. And the problem for many of us is that whether we like it or not, there are lots of biases in the way we collect the data and process it. So we have to be aware of that problem. And so this last but one statement here is rather important. We have to make rational, skeptical judgments. We are not mathematicians. We're using the tools of mathematics. And we have to make judgments. So proof in statistical terms is not what you do. It's a balance between, shall we say, exploration and confirmation. And another useful area is to minimize bias in our everyday work, whether it's industrially, where I've worked, as well as in academia and the NHS. It's also important in research and in literature reviews to actually take out as much of the bias as possible we can't avoid it, but our aim should be to minimise it. And it's also useful in evaluating current knowledge and practice, perhaps more objectively than we might do otherwise. And we can assess publication quality. So when we do, in clinical areas, when we do meta-analysis, we're looking at a range of publications, and we're trying to judge the quality, for example, of clinical trials. And in doing that, we're trying to pull together what is meaningful out of a whole range of clinical trials from many approaches to the same problem. Another area that I'm particularly interested in because of my interest in R&D and product development is in designing data sampling strategies. How many samples, how much data should you collect to get realistic answers to your problem? You're also going to be doing lots of other things. Designing experiments can be done that way too. Now, to start with, I'm looking at some ideas that have come out of modern exploratory statistics. So I'm going to be using some pictures primarily. On the right you've got a table, but what we're looking at here is taking some work which I had to find a way of digging into. This was a collection of data that was acquired by Castings Technology International, who are the industry body for the iron and steel foundries in the UK. They had 30 years of occupational exposure to toxic dusts and gases that they were going to give to the HSE. So the HSE said, we want you to find ways of digging into it and testing whether our legislative attempts to regulate exposure have they worked, and where have they failed? So the data was rather unusual in pattern, and so I had to start by digging into it, and this is a method that you could learn about, starting at the middle of the data and going outwards and seeing how the data spreads out. And this is a way of summarising that. In some ways you have the upper quartile and the lower quartile, and there's the median, and that little box inside the outer box is the confidence interval on that, and the dot is the mean. So this is clearly not a straightforward pattern of data that you would expect from what I might call classical statistics. And I had to experiment with ways of looking at it. So this is a strange plot called a Q-sum plot. It's Goldsmith's Q-sum plot, which is used a lot in industrial quality control. And I used it here to find out when a change in exposure occurred for respirable silica, but I used it only on the higher levels of that exposure to find out what the impact was on the higher levels by changing the upper limit of exposure. And using this technique, we found this peak, which is pretty well where the change occurred. It was slightly after the introduction of the new exposure limit. So it was a way of demonstrating that which you couldn't demonstrate with classical techniques. So a quality control technique turned out to be quite valuable, and it's quite easy to use. Now, a lot of stats that many of you will come across is very multivariate. There's many different variables you're measuring. So one of the things is, this is a series of data that I was asked by my older son to analyse, who is a consultant physician up in Stoke. And it was concerned with renal function. in intensive care. He's both a critical care person and a renal specialist. So this was part of that exploration, so looking at the effects of positive or negative on particular parameters. So here's a way of graphically displaying those influences. I'm not going to dwell long on it, just say pictorially we can represent things. Now, going back to the respirable dusts, this is looking at the whole sequence of the 30-year record and looking at the extreme end, the top end of those exposures, and seeing how the pattern changes. Each of these is for an individual year, these dots. And how the hell do you find a line through that? Well, a guy at Bell Telephone Lab developed, in America, developed a technique called LOIS, which is a sort of non-linear regression smoothing type approach that enabled me to find the trend within that set of data. So it's another way of looking at it besides the Q-sum-span technique, and told more or less the same story, which was rather helpful since we had two different techniques providing me with confirmation of the same observation. I've done a lot of work in quality control, particularly with industry, but I've also done it in collaboration with the Environment Agency. I've worked on techniques for monitoring the water environment around landfills. And I did an exercise to work out techniques for how to spot leaks into the water, the groundwater around big landfills. And control charts were a very useful way of finding out how those leaks occurred, and sometimes you would miss them by as much as 2 years. I did a simulation exercise which meant it had been and gone by the time you detected it. So remember, statistics is an aid, it's not a perfect tool. All these tools have limitations. So different kinds of averaging, this is individual observations and ranges of those. This is a weighted average, time-weighted average, and so is this. So these are ways of showing up changes with different sensitivities for spotting those changes. Very important in industry. If you're doing Six Sigma, it becomes very important. Another area I've worked in is in clinical diagnostics, and here's an interesting plot of sensitivity versus 1 minus specificity, which is known as the rock plot. Rock plots arose out of work in World War II with radar. It's called, it's the full name from the acronym is Receiver Operating Characteristic. So on your radar screen, can you distinguish between an enemy plane and a friendly plane? That's where this all came from. And rock plots are now used in very many ways with imaging and other forms of diagnosis. So they're getting very sophisticated. So these are two aspects of rock plots that one can use, and there's a lot of software around to do that. But we have problems. Sometimes we make false positive diagnoses, and sometimes we make false negative diagnoses. And that's a problem you can't get away from. Some years ago, I had a guy who was a specialist in medical electronics come up to me in a meeting of the Institute of Physics and Engineering in Medicine's Emerging Technologies group and say, "John, I've got a technique for absolute diagnosis of lung disease." So I said, "Di," he was a Welshman, "that's bullshit. That's complete bullshit. There's no such thing as absolute diagnosis." So I got roped in. And that was the machine he began to develop, and I got roped in to help look at. It's a very novel way of looking at lung function. Has a flap valve here, and you blow in there, and at a certain pressure the flap valve opens suddenly. It's like doing a cough. And what you get out of it, you have crossed ultrasound beams measuring the velocity of flow once you open the flap valve. And it seemed able, on some limited trials, to be able to distinguish between types of lung disease that were very difficult to detect by normal means. It had an awful lot of data collected. This is big data now. You were collecting something like 1,000 measurements of flow every second. So this is from the peak of the flow just for the first 2 seconds. So an awful lot of data there from one test on one individual. And one of the things I tried to do was fit a triple exponential to that, which represents how the lung physiology should reflect that. So quickly going through the other things I might have worked on just to illustrate the breadth of applications of statistics. I was head of clinical engineering up at the hospital in Stoke for a while, and I then taught for 13 years on their MSc in biomedical engineering, and each year I used to do reliability engineering projects, which are essentially statistical projects, on the failure patterns of medical equipment in the hospital. One thing we did was look at hemodialysis. So we were looking at different phases of the life and what kinds of failure time patterns were available, and then how did the pattern vary. And this is the pattern looked at over the lifetime of, these are individual times between failures. This is looking at those times between failures over the whole life of a dialysis machine and fitting it to various probability distributions. So we were able to look at failures per machine per year of life, and we were able to look at how the life pattern behaved over the full life. I'll finish now and throw things open for questions.